Classically Greek. I hope they ever be classically Greek. Professor Andreu, we are ready for you. Waiting for
no Greek slang, okay?
I need to find something about hair. Character? It was a pleasure to introduce Angeliki Metallinou. Angeliki got her undergraduate degree from the National Technical University of Athens. It's the best university in Greece, and electrical engineering.
Yes.
And now she's at the University of Southern California, and she's interested in what the general field of affective signal processing, which is really how you can extract through signal processing and computational methods the emotional state of individuals, humans or not. So she's going to talk about that now.
Thank you, everybody. So I'm very happy to be here. I am from University of Southern California, and today I'm going to talk about analysis and recognition of emotional human states, and particularly about multimodality. Can you hear me? Okay. Okay. Multimodality, context, and dynamics, and applications in healthcare. So let me start with some motivation of this overall domain. So, for example, human-machine interaction has become ubiquitous these days, and we see advances in portable, wearable, and smart devices. And you see that human-computer interfaces have become multimodal. We can record audio, video. We have Kinect. We have different physiological sensors. So we can use this information to enrich the way we interact with computers, and we can make the computer sensitive to affective components, so understand our affect and recognize our affect. And we can use this to have more natural interfaces with computers, and they could be, for example, useful in education systems, in spoken dialogue systems, in designing virtual agents. And also we can enrich machine capabilities, so what different machines can do for us. So they can measure signals, we can use those signals to infer behaviors, habits, preferences. For example, one application that some research group and also industry is interested in is remote health monitoring. And another overarching goal of this domain is to try to use computational approaches to better our understanding of human behavior. So expand our existing knowledge from a more computational point of view, and also study both typical and atypical behaviors, such as health disorders and mental health disorders. So different research areas, you can see this field as a combination of technologies from speech and multimodal signal processing, machine learning, statistical modeling, affective computing, and we are interested in recognizing emotional expressions from multimodal information, or general social behaviors, so not only emotions but degrees of excitement, degrees of interest, frustration levels, or depression. Or they're also interested in analyzing not only individual but dyadic interactions or larger group behaviors. And different applications, I already mentioned some of them, in interfacing, smart sensing environments, and virtual agents. And another domain is the domain of behavioral signal processing that tries to find applications of engineering in healthcare and provide tools for healthcare experts. So just before I go to the main part of my talk, because this is a new domain, let me show some background and introduce some of the definitions that we use in this field. So in terms of representations, one can represent emotions as into categorical terms, such as angry or happy. So those are more basic emotions. But we can also use dimensional representations that are describing attributes of an emotional state. So activation describes, for example, how intense is an emotional state. Valence describes how positive versus negative. So if I'm happy, this is positive valence. If I'm angry, this is negative valence. And dominance describes the degree of control or a degree of dominance in a conversation, in a situation, versus being more submissive. And the last ones are used because they tend to be more general for describing real-life emotions that can be more nuanced or do not necessarily fall into the first categories. In terms of databases, This is an emerging field, so we don't have as much benchmark databases are more mature fields such as speech. So we are trying to create those databases. So initially there was a lot of active databases, so we were asking actors to perform a particular emotional state, and that was the data that we collected. Now we're moving more towards elicited and real-life databases. So elicited means that you put people or actors in a situation, and then you ask them to improvise a particular situation in order to elicit certain emotions in the context of a conversation. And real life could be data from real life situations. And I'm going to describe work on both elicited and real life. And these databases tend to be more and more multimodal because of the realization that we are expressing our emotions through these various different signals, and those signals could carry complementary, supplementary, or even conflicting information. So we need to integrate information from those signals. So overall, this research area tries to computationally model and analyze some subjective behaviors, and also tries to learn from domain experts, bring in knowledge from domain experts in psychology, but also bring back to the psychology a more computational perspective on some knowledge that we will gain. So based on this field, my own work explores computational methods to address certain complex aspects of emotional expression. And particularly, how do we exploit this inherent multimodal nature of emotion? How do we incorporate context for emotion recognition? And how do we model continuous emotional states? So how do we use this idea that emotion is not static but can evolve through the course of time and continuously try to track it? And in order to make these things more clear, I'm going to show you some example clips.
I am allowed to use $50 gift card, which you can use any future flights you want to give us. I'm very sorry once again for such a.
Are you kidding me?
Yeah.
Is this a joke?
No.
So this is an example of sarcasm. So as you see, this is a multimodal expression of emotion. Her face is showing happiness, but her voice is angry. So in order to interpret this, we have to use multimodal information. And also we have an airport scenario. She lost her luggage. We see that she's angry. She's becoming angrier and angrier through her interaction, and that is more clear in the next clip.
You're kidding me.
I'm
This is a
really
joke.
sorry.
Do you have any idea? $50? That's supposed to replace everything that I have?
So we see her emotion really evolves through the time. She's becoming more and more intense, and that is some of the attributes that we want to capture, this flow of emotional states. That happens a lot in real situations. So, and the last part of my talk will talk about some computational approaches that we can use for autism research. So in terms of more higher level view, I see my work as trying to discover some context and some structure in these different affective signals, and to use this for recognizing human states, but also to help understanding, bringing back some knowledge about human behaviors and deriving analytics that could be useful, for example, for healthcare. And this work draws ideas from domains such as speech processing or machine learning, but also from domains such as psychology, behavioral sciences. So I'm listing here some examples. So for example, in the idea of context and emotion, it is shown that our interpretation of an emotional observation depends on context, such as past observations, that helps us disambiguate it. Moving on to the main part, this is an outline of my talk. First, I'm going to talk about context-sensitive multimodal systems, then continuous emotional state estimation, and here we're focusing on body language, and finally, on analysis of emotional facial expressions of kids with autism spectrum disorders. So the context work, first of all, what do we mean by context? In this setting, we define context as emotional evolution up to this point. So what was a person's emotional state history? So how have my emotional state have evolved up to this point? And also how I may have been influenced by the emotional states of other people in the conversation. So interactions between different interlocutors. And what people sometimes do in this domain, which is the most typical paradigm, is they have an emotion observation observation, and they have a label, and often this observation belongs to a clearly defined emotional state, such as happiness or anger, so it is pre-selected for certain observations, and then they try to predict the label. In this work, we are trying to look at it from a more general perspective, that we have a whole conversation around this observation, so it might be influenced by past observations, and it also might be influenced by the other speaker. And also, these observations do not have to be very well-defined emotions, so they can be, for example, more nuanced or more general, because in real-life situations, these are the emotions that happen. So for this work, we use representations that are more generic, so we use descriptions of activation, so level of intensity, or valence, in order to process these situations. And also this idea of influence and of context is basically implying a hypothesis that there is a structure in the way that emotional states typically evolve, and we want to understand what kind of structure is there and exploit it for emotion recognition. So this work has been influenced by, for example, ideas from language modeling and ideas such as grammars, but we want to see how they can be employed here. And also, it also implies a more hierarchical way to process emotions. So not only the sequence of frames in a certain observation, but how does the emotion states change from one state to another. And another challenge here is that we want to process all the inputs that we have in our system and not just some pre-selected observations. So the data that we use is the USC mockup database. It contains emotions that are elicited in a context of a situation, such as the example that I showed initially. And it has, we have 10 actors in total. It's a pretty large database for the community. We are freely releasing it, and a lot of people have already used it. And it contains detailed motion capture information from the face, head motion. It also contains microphone speech. And it contains annotations of each utterance in the conversation in terms of their emotional attributes, in terms of angry or happy, but also dimensional labels. So the first thing we try to see is what kind of structure there is in typical evolution. So if we think of a conversation as a sequence of utterances, and each utterance has an emotional label associated with it, then if we assume a simple form like a Markov chain, then we can compute transition probabilities from one state to the other and see how these transitions change. And one could also think of higher order chains, such as second order, or even non-Markov extensions, so use a neural network to process the sequence. If we just use simple transition probabilities, though, even with that, we can see differences in the way that emotional states evolve. So for activation, we see that extreme activation states tend to be more transient and transition back to medium activation. Well, for valence, we see that valence states tend to be more longer lasting. So if we are in a particular valence state, we tend to transition to the same one. And is that a question?
This work, when you say that your results are from a chain,
Yeah.
it's a graphical model that is really strictly for the form of a chain, not a more general model. You cannot jump, for example.
So here, what we do in order to get these tables is we just compute transition probabilities between the different utterances and their labels in the conversation. So it's just transitions between. So given these observations, we'll see how these observations will reflect on our results later. Another way to look at emotion states have to do with a combination of valence and activation information. So we can think of one utterance that we have as a point in the valence and activation space, and we can cluster the space into different clusters that have different emotional information. So if we look, for example, at this cluster, it has more negative valence and high activation, and we see empirically that emotions that fall inside this cluster are more angry and frustration. If we look at more positive valence, we see positive emotions to fall in there, such as happy and excited. And if we look at the neutral to negative valence and low activation, we see neutrality or sadness emotions in there. So this is... Mm-hmm. a dot is one observation that we have one utterance in the conversation that has different labels that are given by humans. So a person watches this utterance, both the speech, hears the speech, and then gives us one observation that is, for example, valence and activation. And we aggregate observations from different humans, and then we get one combined information of valence and activation.
So you haven't told us yet the role of the motion capture.
No.
So we haven't gotten there yet.
No, this is just the labels. So this is the label.
This is a hidden. This is the hidden process.
Yes, this is what we are trying to predict in the end of the day, what we are trying to classify. Yeah.
Just to give us a sense of what these things are, if you could go back 2 slides and tell me a little bit. Had some note at the end. No, one more. Yeah, okay. So you said that the annotations of emotion content per utterance. So each utterance has one of those category labels or more than one?
So we allowed the person to say more than one if he wanted to, but most of the times they just picked one out of angry, happy, neutral, sad, frustrated, excited. They
picked one or more of the categories.
Yeah.
Plus 2 numbers, one for the valency and one for the activation.
Yeah.
And that blue chart that you showed later, for each utterance you have a 2-dimensional point and you just plot it.
Yes,
Right?
yes.
And how many utterances are there total? How many dialogues? You said 12 hours of data.
We have about 5,000.
5,000. So
Yeah.
if I go forward, so let's continue with your talk.
Yeah.
You get to that slide. So there are 5,000 resources.
Yeah. And yeah, it's because the labels was not continuous, they were quantized. Yeah. They were from 1 to 5 in our, yeah.
So the x-axis
Actually,
goes 1 through 5, and the y-axis goes
yes.
higher.
Well, actually here what you see is the average. So it's not 5 distinct values because you can take average of 3 people, average 2 people. And I put a little bit of Gaussian noise around to show the density. Yeah, just for visualization. So that's why you see it into different. Yeah. It's just for visualization purposes. So, okay, so... and one thing that I wanted to point that I wanted to make here is that we make these connections in order to interpret in terms of their categorical emotional content, these data-driven clusters that we derive that have a combination of valence and activation, and we see again how their typical transitions change. So if I am in a certain emotional state, I stay in the same one, or if I am in C1, for example, I can transition to C3 that has variable activation, but it's very unlikely that I'm going to go between states of opposing valence, like C1 and C2. So let's move on to more classification tasks. So here, this is the framework that we have used. So it's a hierarchical approach. So at the lower level, we want to model the sequence of different frames of different observations, like the frames of speech or the frames of motion capture within one utterance. And one utterance belongs to just one emotional state. That's what we assume. And at the higher level, we want to model how the utterance transition between one another. So it has a lot of relations with language modeling in speech. So one approach is to train dynamic models such as hidden Markov models and then score the input utterance into each hidden Markov model that represents one emotional state. And then we have an utterance level feature of log likelihoods. And then we have one utterance for each, one of these features for each utterance. And at the higher level, we are doing Viterbi decoding to see what is the most likely state of emotional states over the whole conversation. So this just assumes a Markov chain here. And if we want, another approach that we tried is instead of training dynamic models is to use, for example, statistics of these features here to get an aggregate impression of the features and then extract useful, the most informative features from them and use at the higher level a more nonlinear approach. So use, for example, a neural network to process the sequence of observations. And we have tried different neural networks that I will describe more later. And we also have a combination of these dynamics here using HMMs with the neural network at a high level, so a hybrid approach. So looking at the HMM, we see that when we do viterbi decoding, we have to wait for the whole conversation to end in order to make an observation about the current state. So that is restrictive. So in order to relax this assumption, we do a sequential viterbi decoding. So we have smaller windows that we do the decoding, and that allows us to have a variable amount of context around the current observation, and also to measure what kind of context would we actually need. And it is encouraging to see that around 3 or 4 utterances around the observation work pretty well for this problem. In terms of neural networks, I will present here results about using short long-term memory neural networks that are an extension of recurrent neural networks to use more longer range dependencies. So those are designed for these longer range dependencies, and also they can learn more optimal amount of history. And if you use 2 layers of them, one going from left to right and the other going the opposite direction, you can have bidirectional information. So looking at some results, here I'm showing experiments, first of all, are organized in leave one speaker out cross validation, so they're speaker independent, and showing results with no context and with context in for valence activation and the 3 clusters that I showed in terms of F1. So F1 is a combination of precision and recall for this task. So if we see how, for example, voice and face work for valence, face is better, and that's a result that we know because face has a lot of valence information like a smile or a frown. Then we combine them using HMMs or coupled HMMs that gives us better information. And then when we add the context, we see that we have an improvement in performance. So all 3 methods seem to work well, and the highest accuracy is given by the neural network. But another observation here is the neural network seems to be less consistent between the different speakers in the database. And generally, speaker-specific characteristics are also very important in this case, and they are causing inconsistencies in the performance. So in terms of activation, we see a different pattern here. So first of all, voice is better here because vocal patterns such as intensity are very informative. But when we add the context part, we don't see any improvement in this case. And we believe that this happens because of the structure that I showed initially. So for valence, we had extreme valence states were isolated instances. So this higher level modeling tends to smooth out these extreme valence states and extreme activation states, and then tends to misclassify them as medium. So this kind of structure is harder to model, and perhaps a framework that would use a detector for these states rather than a context, high-level context work would work better.
What context is doing? What is it actually? What's context in that? To get your extra 5%, what do you really need?
So basically, it says that what is the likelihood to transition? It incorporates the likelihood of transitioning from one state to the other. So if I am angry right now, I'm more likely to be angry at the next time instance rather than be happy, for example. And if my interlocutor is angry, I'm more likely to be one. So this is the extra information that we are using.
Why is it, hard for me to keep up, so why isn't that already in the HMM? And the top half, you just didn't include it, or the HMM structure doesn't support having that kind of a model on a given process?
So the lower level HMM structure has a dynamic structure, but it models the dynamics within one emotional expression. So for example, if I'm saying a sentence that is happy, my facial gestures evolve through that. So it is modeling this evolution. But on top of that, if I am transitioning from happy to neutral, or happy to sad, then this higher level models that as well. And
what Mike is asking is if you want to think about the higher-level model as a language model, which is probably what you said, I think, earlier. Then can't you fold the language model into your HMM structure and just, in other words, why do you have to think of it as a separate thing?
It is an extension of, when we have this, we're just doing viterbi decoding on top of that. So
in one case, you're using a language model, which is the lower half of the table, and the other case, you're not.
Yeah.
So then, so we're getting a lot. I mean, I guess 5% is a lot. So
The other question I had is, you know how we always say that the British have a stiff upper lip?
Mm-hmm.
You know that expression?
I've heard of it.
Well, I mean, they really do. When they talk, one of the great things about the British is, they really do have a stiff upper lip. They could be laughing and crying or saying. Does that show up? In other words, do you imagine that we need to have in this representation? I suppose it would be at the level of the motion capture. It wouldn't be at necessarily at the level of the hidden emotional state process, level of motion capture. We really have to have a nationality-dependent representation. Do you see that?
So we see a lot of difference between how different people express emotions. So if you look, for example, at this variation here is the interspeaker variation, basically. And if we do the experiments without doing leave one speaker out, if we just use some information of the speaker, we can get much higher than this. So, and if you think this database was only American college students, so I think there will be a lot of variation. I don't really talk in this talk about the subject, but we have done work with Professor Carlos Busso on how to normalize features better for this kind of task, for emotion recognition. So.
Would that kind of would it be a couple percent, or would it be another? What is 5% here? Is it a lot, or are you nowhere near sort of the Bayes bound here to this problem?
I think if we normalized, if we had some speaker information, we could easily get another 4 or 5%, because if we have some information about some baseline about the same speaker. But this was more from the perspective of a more general system that you don't know the other speaker. So
when you're looking at these numbers, they're a little bit hard for me to interpret because not having seen the examples where the system made errors, I don't know whether those would be reasonable errors for an annotator to make or what kinds of things it's missing. So you haven't mentioned what the inter-annotator agreement was to start with.
Yes. So for this case, for the activation and valence ratings, we saw that most of the people were within one rating apart. So if you rate from 1 to 5, I think for valence like 95% or 90% were saying 1 and 2. And the other one was 1 and 3. And because we have more than one people, we are basically averaging around them. So this is an idea of annotator agreement. And about the errors that it made, I mean, I think it's hard to say that, but a lot of cases had to do with things that expressions could be very nuanced and could be very nuanced. So, for example, sadness that could be misclassified as neutrality or things like that, or things that are sarcasm that I showed initially, so things that are similar to that.
So did looking at the errors suggest any additional features, either in the voice or the face, that maybe would help you uncover those subtle distinctions? And you cited Ekman before, so he'll tell you should be looking at individual muscles in the face, which are hinting at people's actual emotions, and they can't just in the first moment before they compose themselves and they start speaking.
Yeah.
And you could decide to look for those kinds of things.
So in order to try to select the features, we try to select the ones that seem to be most informative for emotion classification. So in that way, for example, we are looking at correlations of features with a label that we want to have, or correlations of features, and also features that are uncorrelated with each other in order not to have a redundant model. So through this, we might hope to select features that are informative for different tasks, for different emotions.
Yeah, I'm still trying to get a sense of what the features might be.
So I'm not really describing the features here. So for example, the features have to do with different facial points. And we are also basically, so we have a high dimensional representation of different facial points. We are trying to reduce the dimensionality by excluding facial points that are very correlated with each other. So if I have 2 points here and I move, they will be very correlated. So it's okay to get just one of them. Or if I have points that are very mirroring, then they are usually very correlated with each other, so I can get just one of them. So this is the basic for the features that we used. When we used the derivatives and the statistical functionals, then we had a variety of statistics of certain features like that, and then we tried to select the most informative ones. So I have a 3-state HMM, and it's
Literally three-state away.
three states, and it's fully connected. Yeah, so we are assuming, we don't assume left to right. We assume general transitions within that.
And so then these pictures must be steady state. I mean, you have for every emotion or whatever trying to extract, you assume there's a steady state. There's 3 steady states that you're transitioning from one to another. You're not really doing transient. I mean, you're not extracting transient.
Well, but there's derivatives among the features. So if you had a
Yeah, I'm using derivatives, yeah.
so if you had a culture where you expressed anger by getting steadily softer or something.
Right.
Yeah.
Okay, very good.
Okay, so should I move on? Okay. All right. So let me just mention a little bit more extension of this work for having 2 speakers and having a conversation, for example, between how to incorporate influence of the other speaker. So again, you can have the inputs here between the 2 speakers that could be different modalities. You can train your models. And the difference what we do here is instead of just collecting the score vector distribution, we also model the distribution of the score vectors as well. So we trained another model on top of that to model the distribution of a current observation given the emotional state. So for example, if I have emotional states that are ordinal, such as low, medium, high, I can have train a logistic regression that will model this distribution. So then I can think of the higher level processing, such as a hidden Markov model, where the emotional state the state of the hidden Markov model, the observation probability is this distribution that I modeled here, and the transition probability is the bigrams that I have computed. And this way I can model more flexibly the conversation, even between each speaker separately, but also during the dialogue. So for example, we found that using a higher order Markov chains for that will take information from both my previous state, but also the other person's previous state would work well. So just an overview that this allows us to consider interlocutor influence. We experimented with fusion at different levels of the system and trained the system discriminatively. So we tried to make a system that would be more applicable to a real-life situation, that you have continuous inputs to the system and you're trying to get a decision out. So in terms of future work, this is the last part. I would be interested to examine notions of context that are a bit more broad, such as, for example, what is the conversation topic, what are they talking about, and I think that could also help us to improve our performance. And this is a modality that we haven't considered yet. It's basically language. And now moving to the next part of this talk, I'm going to take a different view. So in the previous work, we are assuming that our emotional states are structured around conversations. So each utterance has an emotional label. But what if we have a more freestyle interaction of people in a room, and where don't assume that our unit now is the utterance? So in this case, we don't know exactly what would be the unit to model this interaction. And for this case, we can also assume that the emotional state of the user may flow through the course of time or may change through the course of time. So when you have 2 people interacting in a room, they have multimodal information that is continuous between them, and their activation levels or their excitement levels can change and be a continuous variable through the course of time. So this is what we try to model here. This is the view that we take, that we look as emotion as a continuous variable that is expressed by a continuous flow of multimodal information, and then we want to estimate it. And this is in contrast with other work, for example, that look at certain units or look at an overall impression over a whole interaction. Here we want to have more detailed information. And this, of course, gives us a more flexible representation, but at the same time, it has challenges in terms of how do we annotate these emotional states, and we found that it was actually very hard for humans to do emotional annotation, and I can talk more about that if you like, and also how to make frameworks that estimate, say, their continuous emotions through time. And just to give you a perspective here, this seems to be an emerging direction in the field. About a couple of years ago, there were few people working on these representations. Now there have been, this year, workshops on this and a special issue on this that we participated. So another part of this work that I find interesting is the focus on body language. So body language has not been used as much in the emotion recognition community, but is a key modality. It's very informative. So we know that approaching or avoiding or touching or gestures, we know that they are very useful for recognizing emotions. Also, we know from psychology that body language is an indicator of dominance in a conversation, and also that there are works that also cite that body language can even be more discriminative than face for emotions. So here we try to look at body language in the context of dyadic interactions, and we are looking at emotions such as how is body language modulated to express emotion, and which body behaviors are more informative of different emotions, and we're looking this from a dyadic interaction perspective. So not only how am I, what body language I am doing, but also how am I changing my body language with respect to the other person. So if I'm moving towards him or looking towards him, etc. The data that we have used is the USC Creative IT database. We collected it at USC. It's a dyadic and multimodal database and contains more freestyle, dyadic theatrical improvisations. It has a very rich variety of emotions and multimodal manifestations, and I think it is rich for doing different types of analysis here. So not only emotion recognition, but we are currently working on many other things with this data. So we have full body motion capture, and we also have microphone speech. And we will release it very soon. We are organizing the data. So this is one example. And here is the motion capture that we have. So this to give you an idea of the data. And now one challenge that we have is, given this data, how do we annotate emotional content? As you see, the interactions are very complex. And as I explained already before, that's why we use continuous annotations through time. And we annotate for each actor separately and for each recording for activation, balance, and dominance. And as we found, this is a very time-consuming and very challenging task for humans to do. I can say more about the challenges, but I'd rather move on quicker and just say that we had 7 experienced annotators to do this. We had through several iterations of designing the annotation, and in the end we had at least 3 people per recording. And just one example of how they might annotate, you can see here the interaction, and you will see here the annotations from 3 different people of activation of the male actor.
Too busy. I'm too busy.
So as you see, the activation seems to drop for all 3 cases. So the 3 different lines are 3 different people who are doing a rating. And you see that they agree on this trend, that there is a drop. But some of them may disagree on the absolute value of that rating. And we generally see this trend that annotators tend to agree more on the trends rather than the absolute values. And they're easier to rate in terms of comparison rather than absolute values. So this is an overview of what we did. We started by collecting this data. Then we used the motion capture to extract various features. We used speech to extract various features. And we used the videos to extract different annotations. And in the end of the day, we have a set of continuous random variables that are the continuous multimodal information that we observe. And we also have a set of random variables that are the underlying emotional states. And given those features, we want to estimate the more likely emotional state. Yeah.
What features did you use for motion training?
Yeah, so I'm just going to describe that right now. So we decided to go for knowledge-driven features for this particular approach because we wanted to connect back with psychology work. So we looked at things that supposedly are informative in terms of body language. So things such as postures, velocities, absolute velocities, orientations, whether you're looking, whether you're moving towards, things like that. And you had an exhaustive set of features, and then we tried through feature selection to see which are the most informative ones for each task. And here I'm just showing some examples of those. Another thing that we did is we tried to do some analysis of those features to see how they reflect different behaviors. So for example, if we see people who are highly activated versus low activated, then, for example, we see that highly activated people have higher velocities of arms and feet, as one might expect. In terms of orientation, we see that people who are more activated tend to lean more towards the other person, tend to move towards the other person, and orient themselves towards the other person. In terms of hand gestures, they are very important. People who are more activated tend to have their hands further away from the body, raised higher up. And body location was also important. People who are more activated tend to be in the center of the recording space, less activated moving the corners. So these are some examples that also they are more intuitive, and also they seem to agree with psychology work. So looking at, yeah.
I'm sorry that you don't have, I'm surprised you don't have distance between
we do have distance. Yeah, we do have distance as well. So this is not an exhaustive list. This is just some examples that I show. And actually, if you look at the paper, we also do the same analysis for other body language behaviors, such as dominance, and we see what features are important for there. So for example, for dominance, you would see more features that are relative, because dominance is a relative behavior. So a lot of features that have to do if I'm moving towards you, if I'm moving my hands towards you, if I'm leaning towards you, this kind of things would be important for dominance.
Would you be able to get the difference between you pointing at my face and you pointing at my feet?
With the data, with the information we have, yes, we can get that.
Right, but do you have such features? I'm just curious.
So we have features such as what is the location of your hand with respect to your body, and so the 3 coordinates. And also we have the location of the other person, so it contains that information, the combination.
You're like pointing or something.
Oh, the actual point,
It's a particular gesture that you might pick up because it has a particular cultural meaning.
Yeah, no, that we don't have because
Face or something is very, assertive.
we don't have that because we don't have the actual information in the fingers, right? Yeah, but actually, for example, for dominance, we found that an important feature was touching. So people who tended to be more dominant tend to try to touch the other person or be very close to him. And people who are more submissive tend to do the opposite, like move away. So,
Let me ask about the body location. Isn't it more feature of that movie or the corpora than of the people?
You mean if it is specific to the corpora?
Yeah, because the human doesn't get more agitated or activated if he moves, to left or to right.
I think more this has to do with whether you are in the center of a place or towards the corners. And I think that also has been found as an observation in psychology, that people who want to be center there seem to be more active in what they... Or they try to be in the center of an interaction. But I mean, I guess it also depends where is the center of attention. For our recording, the center was the actual center of the recording space. So sometimes we saw, like in the video that I showed initially, when the person became less active, he tried to move towards the corner and the other person was following him. So... All right, so I think I'll try to move a little bit faster through this. So the tracking that we do is basically trying to derive a mapping between the continuous observations that we have and the underlying emotional states. And this is an idea that has been used, for example, for things such as a mapping between articulation and speech acoustics. And we use this here to map between underlying states and observe features. So we can train a joint model of X and Y, where X are the features and Y is the emotion, and then we can do maximum likelihood estimation. In order to incorporate dynamic information, so the idea that these variables are smoothly evolving, then we can add higher order derivatives in these features, and we can basically estimate their statistics, the behavior of the derivatives. So again, we can do maximum likelihood estimation. We're assuming a Gaussian mixture model in our modeling, and that means the conditional is also a Gaussian mixture model. and we can solve this via expectation maximization. So this is the more core algorithm that we use, and on top of that, we have to incorporate the fact that for our data we have a variable amount of information, so people are not always speaking, they might be just moving around, so we compute different mappings according to the information that we have, and we use them appropriately. Another thing has to do with the resolution at which we choose to do the tracking. So we have very detailed information at each frame level, but for this case, because emotions are more slowly varying, we see that this level of accuracy may not be necessary. So we do the tracking at larger windows, so windows of 3 seconds with 2 seconds overlap, and we assume that the emotional state is the average over that window, while our features could be a more rich set of functions of our raw features of that window. So we have a more higher level information there. And I just showing here that this code, I have released it, and we are preparing the data for release as well. So as a baseline, we use neural networks that are trained for regression. And we use this particular one because it has been shown in a parallel work that it works well for the problem. So we decide to use it as a baseline to compare with existing work. And so our results, I'm going to go very fast here and just say that the first thing we need to notice is the annotation correlations. So we see that they're actually around 0.6, and that shows the difficulty of the task. So if you ask basically 2 people to do the annotation for the same recording, that's on average how correlated they will be. So this is something that will limit our performance. When we try to do the activation, we get around 0.5 with what we are proposing, and we see that for the other attributes, it is even harder than that. So dominance is less, and for valence, we're not doing well either. So, but when we add speech for activation, we are around 0.6. So this is encouraging, since we are reaching basically what humans can do for this task. And again, we are better than our baseline. For dominance, we have moderate results, so it helps to add speech on top of that, but there's still room for improvement. And for valence, we are still low. So the reason why valence doesn't work that well, it's again a working hypothesis we have, but we think that valence could be something that is at a higher level. So we might need to use higher level features, or features that are summative over the interaction in order to capture this attribute. Some ongoing work that we do has to do with body language analysis and generation. So we want to use this database to have also generate full body virtual agents. And there we are looking at aspects such as how do different people influence each other in terms of their body language, in cases that they are friendly with each other or in cases that they're unfriendly with each other, and how can we use this information to generate affective agents that may be friendly or may be unfriendly, or in this case. We also want to work more towards saliency detection. So if we have these continuous estimates, then we can pinpoint the parts that you have an abrupt change and look at what is happening in these points, what events are going on. And I think this framework could be also useful for more other attributes, such as the level of frustration of a user while he's interacting with a machine, or the level of interest, or etc. So this is the last part of my talk, that I'm going to talk about applications in healthcare. It's more an ongoing work, so I'll try to be brief. And so let me just start with some motivating facts about autism. It's a condition that affects 1 in 88 children in the US, and it's characterized by a variety of symptoms, including difficulties in social communication and reciprocity, repetitive or stereotype behavior, and it's actually a very complex condition. And there is interest to see what technology can do for autism spectrum disorders. So the work that I will describe here falls more in the first part, to try to understand certain patterns of communication, of expressions of those subjects. And I just want to mention that one challenge with this project was that it is such a complex condition that we want to figure out how to pose the problem in a way that it won't oversimplify it, but it will provide some meaningful information back to the psychologist. So the work that you see here is more geared towards analysis, towards visualization, towards understanding, rather than trying to classify, because we are quite far from that yet. So we know from psychology that facial expression expressions of kids on the spectrum tend to be considered more atypical or more awkward, and we want to quantify this sense of atypicality. So we will use statistical techniques and motion capture to do that in the hope to get some quantitative insights. The data that we have is from 37 children, 21 are with autism and 16 are typical. They are collected by our collaborator, Professor Ruth Grossman at Emerson College and UMass, and we have detailed facial marker information on their faces. They do facial mimicry tasks. What that means is they watch one video and then they have to imitate it. So for example, they watch this video, and they have to imitate this response. Or this response. And for our analysis, I'm just going to go quickly. We use ideas from functional data analysis in order to represent this time series. So the main idea here is that we transform our raw data into some functional form using transformations such as this one. So instead of having this time series, we use it as a function, and we decompose it into a set of basis function and, for example, coefficients of the expansion. So, for example, this could be a Fourier transform, but here we are using B-splines are basis functions because they are more appropriate for non-periodic time series that we are looking at. And this will allow us to do some smoothing over the low-level these features, but also better calculation of properties that we need, such as higher-order derivatives or FPCA analysis that I will describe later. So generally, we looked at things that were inspired by psychology. For example, we know that people on the spectrum have more asynchrony in the way they synchronize their modalities. We looked at asynchrony in the face between the left and right part of the face and upper-lower part of the face in terms of correlation. We looked at roughness of face and head motion, so how jittery or how rough are those. And we found that people on the spectrum have more asynchrony, and they also have more roughness of face and head motion, and this could be certain indications of what is atypical. In terms, another line of work has to do with analysis of particular expressions and how they are realized differently by different children. So if we think, for example, of the expression of a smile, we can describe this expression as the distance between, for example, the corner of my mouth and my cheek. And every time I smile, this distance becomes smaller. So if you see here in the blue line, we have two smiles, so one after the other, so we have two valleys. In the red line, you can see a more atypical realization of this expression. So you still have these two valleys, but you have a lot of variability here from a kid that is on the spectrum. So this is the type of realizations that we're looking at. And we want to compare the different realizations that we have from different subjects of the same expression. So the first thing we do is we align them using landmarks in order to align basically the two valleys. And then we do a technique such as functional PCA that basically tries to deconstruct the variability of these expressions. So it takes as input some curves, and then it calculates eigenfunctions instead of eigenvectors that basically are a decomposition of the input curves into an orthonormal basis system that will maximize the data variance. And one thing that we can do is look at the coefficients of this decomposition. So for example, 1 versus 2, 1 versus 3, and 2 versus 3. And one observation that we can make here is that this decomposition is more variable. So kids that are on the spectrum have a greater variability in their expressive choices that they employ, largely because of idiosyncratic face gestures. So that agrees also with psychology work that tells us that people on the spectrum have a large variability of their symptoms and of their behaviors. So this is just some examples of the work that we are doing. This is still ongoing work, but we are hoping to bring you insights into the autism domain. Other directions that I would like to follow have to do with analysis by synthesis. So I would like to use some of this data for facial animation and for showing differences between typical and atypical expressions, and perhaps transforming from one expression to the other. That could even have pedagogical purposes for kids that could be on the spectrum, like an assessment, for example, facial expressions. And generally, we want to provide tools for autism researchers. So some other parallel directions, one I already mentioned, is about normalizing features to account for interspeaker variability in emotional expressions. This is joint work with Professor Busso. I've also worked on discriminative structure, belief tracking for spoken dialogue systems. That was the same work that we did at Microsoft Research. And finally, this is just an overview of things that I am thinking as future directions. It's in terms of affective computing and continuing the work that I did on analysis and modeling emotional expressions, in terms of extending this in dyadic interaction and larger groups of people, in terms of spoken and multimodal interfaces, for example, looking at affect-sensitive agents and multimodal sensing environments that can recognize such information. And I'm also interested in continuing this work on behavioral signal processing and healthcare applications. And just some final things about this area. It has a lot of rich problems with both theoretical and practical components. It is interdisciplinary and it has a lot of room for collaboration between different people. And also it has exciting technological and societal possibilities. So this is the end. Thank you very much for your attention. Yeah. So the framework that I showed in the first part of my talk, the last one, it allowed for basically integrating at each layer of the classifiers that you wanted. So if you wanted to integrate, we could either train different models and integrate them at the very end. So this way incorporate asynchrony between the different modalities. So for example, we found that certain modalities are more correlated than others. So face and voice, especially because of lip movement, are more correlated with each other, and we tried things such as coupled hidden Markov models to integrate this asynchrony. But for example, things such as head motion and voice are less correlated, so you might want to integrate them in the end. So these are some observations that we had.
That was really nice. Mark, I know we interrupted you a lot.
No, it's okay. You can ask me more questions. Yeah. Okay. Yeah. Thank you. Yeah, I'm very excited about Kinect these days because I think a lot of these things that we did, when we did this, we didn't have Kinect, but now we can redo it, and I think we can get rid of some of the constraints that of the motion capture that poses.
You know, there's a world, sort of one of the best groups in autism is right here at Hopkins. Autism speaks really slow.
Okay. Yeah.
How did you get connected to all these, you have a collaborator in Texas and you have a collaborator in Massachusetts. How does that happen?
So that's through my advisor. So Professor Sri is, so we have a collaborative grant with different universities that's called Expeditions in Computing. So that one is between like UIUC and Georgia Tech and MIT that we're looking at these problems. And but this particular work, Professor Grossman directly contacted us because she had the motion capture data, but they didn't really know how to process them, so they needed our help. So that's how we got involved in that one.
Pioneering work, how do you know that you are making progress? Are you comparing with other people or are you comparing with yourself? I think it's related to the
Yeah.
And it's like, so is 50% good? Or
Yeah.
is really 80%?
Yeah.
Is somebody buying this?
Yeah.
Or, are they happy that you already met, or that can you go back to the lab and work on it a little bit more? I'm not in this field, so I'm really curious.
So-
how you evaluate yourself?
So that's related to the thing that I mentioned initially, that there are no benchmark databases yet for this task, and there is something that we are trying to get out. So in order to evaluate, for example, what I am doing, I tried to look at what people are in the field doing and implement this for our database. Because for this database, I didn't have numbers of people looking at all the sequences. Even when we released the database, what people usually did is they took the observations that were belonging to specific categorical labels, such as angry, happy, and they did 4-way classification or 5-way classification. So I couldn't really compare, because I think that time no one had done that. But then I looked at the most common techniques that they used, and I didn't use all of them here, but for example, SVMs or hidden Markov models, and then implement on top of that this. So for the second work, I used as a baseline something that was proposed for that problem. So I wanted to find a way to compare with what other people are doing. So that's why I chose that baseline, for example.
I think there, so most often you are comparing, if you are telling us how accurately you do things, to some data which were provided by human agents, right?
Yeah.
And we have the same problem with speech recognition. How do I know that what I'm getting is actually in some ways meaningful? How do I know that emulate what a human ever thought that was good is the best thing? Or is it, maybe I'm asking, are there some already applications for this that I can go and buy it in Radio Shack? Or not?
For recognizing emotion state. I think...
or is it still too much in the lab?
Okay, so the first thing you asked had to do with annotation. So I think one thing that we can try to do is take, for example, look at the evaluator agreement, or take a subset of the evaluators that agree. Or, for example, there's a lot of work going into, for example, crowdsourcing. This seems to be interesting to just use a lot of people to get a variety of annotations and then try to select the ones that seem more reliable. And we are trying to move to that direction as well for these databases. So the second part, to use it in real-life applications, I think it hasn't been done yet. But I think it is, because there are a lot of groups working on this, I think we are very close to doing so. Yeah. Yeah.
From that point of view, I guess there's a question about whether you should be building on top of that stuff. So I'm thinking of the CVPR best paper a year or two ago where we talked about classifying, I guess, pose recognition and connectors. Yeah, it was decision products based on synthesized data combined with motion capture. And so if they can actually extract those things from you, for you, does that mean that maybe they're doing a very good job because they have more training data collected because they have a lot of money? Could you use their extraction to build some kind of higher level model?
Yeah, that would be great. Yeah, that would be great. I mean, for me, I think I am really excited, for example, to see how we can integrate features from Kinect in these technologies. And
so if somebody relieved you of the burden of doing signal processing and was able to track, gestures,
but even
an inventory of gestures, and so that you could move to larger temporal windows, what could you say about the dynamics of an interaction?
I don't see necessarily as relieving. Okay, first of all, I mean, even if you have the Kinect gestures, the Kinect raw data, for example, you still need to think about what you want to extract from this. So I think one guidance for us is the features that we found informative. And for example, we find informative general motion features, orientation features, so we can focus our attention to extracting those from example, from Kinect sensors. And then I like the idea of looking at larger temporal contexts as well. So some of the ongoing work that we are doing is we are trying to approach this problem of continuous gesture data that we are getting from a more discrete point of view. So trying to segment them into basic units, like gestures of my hand, and trying to see how these basic units relate with each other and relate between the two people. So this is a little bit has to do with the work that I said about the virtual agents, because one application of this is to use it for animation for that. So, but we are still in initial steps of this analysis, but I find it very interesting. Yes.
I think we wrap over. So I think that's because perhaps
We were having too much fun.
I know. Let's stay here for an idea at some point.